Okay, today we're going to talk about current loops in magnetic fields and talk about torque. Now these are really important in our daily life because this is the basis of energy generation, electrical generation. Every electrical energy source besides solar energy uses some sort of rotational mechanism to create electricity within a magnetic field. And we're going to get to that more fully in the next, when we talk about Faraday's law. But right now we can get the idea of torque and what's going to go on in it. Okay, so let's imagine we have a rectangular loop. So we talked about some circular loops, and we're just going to talk about a rectangular loop to keep the geometry simple. So here's a rectangular loop of wire, and I have it pinned along an axis. Okay, and I've got it set that current can flow in around this loop and flow back out. Okay, so I've got current flowing around this loop. All right. Now I'm going to place it in, let's say, a huge solenoid where I have a uniform magnetic field going through it. Okay, this is all uniform magnetic field. Okay, now this 3/4 view is supposed to help, this is the axis that's going to rotate, but it's going to get really complicated to see the directions if we try and keep it that way. So now I'm going to draw this as a side view, as if I'm looking down the axle at this. And that picture is going to look like this. Here's the axle, and I'm looking straight onto that wire loop. Okay. Now current's flowing out across the top. That means across the top I see current flowing out at me. So that's the dot. And in the bottom, current should be flowing away from me. It flows there and flows back this way. So these are the currents flowing, and then current flows down in this wire that's closest to me. It's going to flow up in the wire farthest from me. Okay, now everywhere here, but most specifically here, okay, here we have this uniform magnetic field. Now that field's actually everywhere, okay? It's along these wires as well, okay? It's everywhere. But I'm going to focus on just those two locations, okay? Now our goal is to figure out, well, what is the net force acting on this? And we're going to see that the net force is 0. So let's check that really quick. Okay, so if I look at the top wire here, okay, current's flowing out, and the magnetic field's this way. So I have current flowing out at you. That's my green. The magnetic field is to the right, which means my force on that current is upward. So here is F on the top one. Okay, now let's flip this around. On the bottom, I've got current flowing into the page. Okay, so my green is flowing into the page. The B field is still to the right, which means now my red, or my force, is down. Okay, so I get a downward force. And because the current's the same, the angle they make is the same, then it should be an equal force, which means there's no net force there. Likewise, if I look at this wire, the current's flowing down that way. Okay, the B field has a component. The B field's this way, all right, and it has a component perpendicular. So I can break this into a piece. This field can be broken into a piece parallel to the current and perpendicular. So it does have a perpendicular piece. Okay, and that would give me a force outward. And if I did the other side back on this one, then it would give me how to do that. It's the field's that way. Anyway, the red is down. So the force on this wire closest to me is going to be outwards. Hard to draw on this picture. This one's going to be inward. So the net force on this whole thing is 0. Okay, everything's pulling 0. But look at this force and this force. The forces along the axis aren't going to do anything. The axis kind of fixes the wire. It can't move along its axis. Okay, but if it can spin about that axis, then this force is going to have a torque that's going to cause it to rotate that way. And the same could be said about this one. So these will actually, though the net force is 0, the net torque is non-zero. These work together to rotate this thing in the same direction. And so our goal is to find out, how's that related? So let's just talk about torque in this case. All right, so I know torque is a distance from a pivot point to where a force is applied times the size of the force times the sine of the angle between them. So I need to be careful. Here is my R, and I'm going to extend that out because the angle between them is right here. So that would be the theta I care about. All right? And so the torque is going to be equal to the force, which we now know the force on a wire is ILB. Okay, and if we assume this is a square loop of length L, right? And that's the force up there. And then R is going to be from the pivot to that, so that's L over 2. And then theta just depends on what its orientation is. So that means my torque on the top is equal to L over 2 ILB sine of the angle between them. Okay. Now, for the bottom wire, okay, we could do the same thing and find that it's going to be the same size, same length, same B field, and makes the same angle. So it's going to be equal to tau top. And so tau net is just twice this, so I can get rid of that 2. And I end up with an IL squared B sine of theta. Okay? All right, well, L squared with the square loop is just the area. That's IAB sine of theta. And we've seen before for a loop that IA is just simply its dipole moment, which we give by the symbol mu. All right? And so this could be true actually for a circular loop or an oval loop or any loop or a molecular loop by knowing what the dipole moment for that loop is, okay, for that element. And so now we have, in just in terms of the dipole moment, we can find the torque on that dipole because of an external field and how it aligns with that field. Now we could take this one step further and talk about a vector nature of this mu. Okay, if we define mu, the direction of mu, to be given by the right-hand rule for this curling loop. So this is where my hand's a little bit better. The current's curling around this loop, which means the thumb points perpendicularly away from the plane of the loop. Okay? So in this case, mu points like this, and we give it a vector nature. Okay? Now I'll leave it for a geometry problem. I'll leave you to do the geometry, but if B points horizontal, the angle between this normal and B is the same as this angle here. Okay? I'll let you play with the geometry to show that. But those are the same, which means the angle between mu and B is theta, and this can be rewritten to say mu cross B, because mu cross B means mu times B times sine of the angle between them. So now we have a way of talking about the torque on a dipole as a full vector in a very simple way. First, find its dipole moment, either molecularly or find its current times its area, and then find out the magnitude of the magnetic field, and then find the angle that they make with each other. So we can see as they get more and more perpendicular, the stronger the force is, and when these are parallel, the force goes to 0. So let's take a look at that case. So first of all, this is really important. I'll box that in. Think about that. Let's take this. Once this is rotated a little bit, it'll get eventually to this point. Pivoting about that point. B field's still pointing to the right. That's from something else. Remember, that's a source from something applied, like a big solenoid. And so now, if the current's flowing out, B field, force is still up. That didn't change. And I could do the same thing. The current's going down. B field's to the right still, so force is down. And that one has no net torque. Okay, so if that's how it is arranged, it wouldn't move from there. That's actually its equilibrium position. And so we can see that that's the case where mu aligns with B. So often we talk about how dipoles and magnets, they want to align with an external magnetic field. That's why. If I have a bunch of little iron filings, they're all like little magnets. And if my B field is pointing like this, some external applied B field, well, guess what? These will all eventually want to line up with this external B field. So that is the torque on a loop, which has very important implications for generation of electricity, which we'll see more so in the future, and even on molecular interactions, which happen in medical imaging and in material decomposition to figure out what material is made of. Very important principle here.